especially the people that are full online. So, is that on?
Yep.
We good? All right, awesome. So, let's go through this real quick. So we've got, it's really blurry here, but this is a -3 oxygen 16 here, right? So how many protons are in this oxygen? What do we think?
8.
You have 8.
Okay. Which table was
This is the second one. This is the second one.
the ion?
Yeah, the ion one. Mhm.
Oh.
We're going over the ion one because it might be a little harder than the other one, so I just want to go over this one real
So
quick.
what's the number of protons?
Yeah, what's the number of protons in this oxygen right here?
8.
8. So I have 2 8s. Anybody else think differently? No? Yeah, so it's 8. Remember, number of protons is kind of unique to each element, right? So oxygen is always going to have 8 protons. If it's an oxygen, it is always 8. Same with like nitrogen. If it's nitrogen, it's always 7. Carbon, always 6. Alright, number of neutrons. How many neutrons does this have?
8.
8 as well. How do we know it's 8, Taylor?
Oh, because you're supposed to, the number of like actual neutrons there are, you're supposed to subtract 3 to. Wait, I think.
So what number are you subtracting from, right? What number are we talking about?
You're not subtracting from the number of neutrons, but from the atomic mass, I think.
So, the atomic mass. So, what do we have on the table here? We have the 16 right here. What is the 16? What is this number?
The isotope,
It's not the isotope. What's the name of this number right here?
mass,
Mass
number.
Yeah, mass number. So the mass number represents what?
The, height, how.
So there's 16 of them, right? We know that. So you said there's 8 protons, 8 neutrons. What does that 16 represent?
The protons and the neutrons together.
Yeah, protons and the neutrons together. Yeah, exactly. Combine them both. So the reason we found the neutrons to be 8 here is because we have 16. We know there's 8 protons in the atomic number of oxygen. So we subtract 8 from the mass number. We figure out how many neutrons we got. Make sense? Awesome. How about electrons? How many electrons do you think we have in this atom over here, this ion that we've got? How many electrons?
3. Ooh.
We got a lot different. Okay, so I heard a 5, I heard an 8,
12.
I heard a 12. So 5, 8, and 12. So why do you think it's 5?
The O, -3, I think the -3 means how many more electrons it needs to be balanced. And
So how many more it needs to be balanced is what you're saying?
I think
You're in the right direction. So I think the thinking is right, but the number of electrons on your side is wrong. So let's talk about this for a second, right? So if I got 8 positive charges here, and I have 5 negative charges, you know, in the electron cloud. Imagine this is the electron cloud on the outside, right? So if I've got 5 negative charges and 8 positive charges, what's my like net charge on this?
Like, is it positive or negative?
Yeah. So how negative or positive is this right here?
This is a positive.
Positive by how many charges? By 3 charges, right? So if that were the case for this oxygen right here, would that be a -3 or would that be a +3? Be a +3, right? Because again, we're talking about ions. So if we wanted to make this a -3, if we wanted to say this is a -3 ion, how many electrons would we need on the outside here? 11, right? Yeah, exactly. So you're adding. So basically, with electrons, you're always either adding or removing electrons in order to see that charge on that ion right here. So because it's -3, this is a little confusing because we're adding ions to make it negative, or sorry, we're adding electrons to make it negative, but remember electrons are always negatively charged, right? So if you're adding negative, you're going to make your thing more negative. You're going to make your ion more negative. I shouldn't say thing, I should use proper scientific words and vocabulary. But yeah, if you have more negatives to your ion, you're going to end up getting more negative ion. Does that make sense? So our electrons here, 11. So what about our mass number? We kind of already talked about this, but what is our mass number here? 16, right? And then, is this an anion or cation? Anion. Make sense? Alright, so let's do the rest of this. I think that's a plus. I can't tell, it's so blurry on here. Yeah, it's a plus. Okay, so let's go through this one again. Oxygen, how many protons? 8. How many neutrons? 8, exactly. We haven't changed anything here. Mass number is still the same, we still got 8 and 8. Electrons, how many do you think we have? 7. Why 7?
Because it's a positive one, so that means you need to have -1 electron.
-1 electron, so yeah, you basically remove 1 negative charge. You have 8 positive charges in the nucleus, 7 negative charges on the electron cloud on the outside, so you have a +1 ion. Yeah, exactly. Mass number? 16. Anion or cation? I heard both. Was it anion or cation? Cation. Okay, cool. I think maybe I just heard cation and everybody said cation, but I heard both. I don't know. Alright. Last one here, or last two here. So a negative carbon ion here. How many protons? 6. How many neutrons?
6.
How many electrons in this one? 7 in carbon +1?
That's a minus.
Oh, it's a minus? Oh, it is a minus. That looked like a plus to me. Yeah, you're absolutely right then. Yeah, my bad. 7. Alright, mass number. What do you think? 12. Anion or cation? Gotcha. Looks like y'all pretty much got this. So we'll blitz to the last one here, and then we'll go into our stuff that we're going to do for today. This is the +2 one. That's what I was getting mixed up with. So, protons. How many protons? 6. Neutrons?
6.
Electrons?
4.
4. Yep. Mass number?
12.
Anion or cation? Cation. Did we get all of this? We're pretty good on that. Awesome, cool. Yeah, and just again, a quick rule of thumb basically is if you're messing with the protons, you're changing the element. If you're messing with the neutrons, you're making isotopes. If you're messing with the electrons, you're making ions. That make sense? Good. All right. So we'll go ahead and get into what we're doing today. So, if you go in Classroom, I posted an assignment that has a link to an online activity. So, we've been talking about the atomic mass, but we're going to kind of figure out why we get that number for the atomic mass. So, just a quick little guide for you. We're only doing one of the activities because I wouldn't do the other activity, but that other activity just kind of introduces what an isotope is, and we kind of already know what an isotope is. We kind of got through it. If you want to click through that activity, go for it. It'll show you what isotopes would be stable versus unstable of certain elements. So it's a neat little simulation there as far as that goes. But yeah, so just a guide here. If you have that, you all see the link online. It's like, Carson, you got it. Just let me know if y'all get to that. But yeah, basically the questions I want to know is what determines an element's atomic mass, and then have a little bit of a math question on the bottom here. That's the second question there. So we're going to spend about, I'd say 10-15 minutes trying to figure that out, messing around with the simulation, trying to answer these two questions. Yeah, so click on the mixtures one. So isotopes one is shows you can add proton, or you can add neutrons to an element, and it'll be this isotope is stable, this one's not, etc., etc. So it's a neat little thing. I was initially going to use it to introduce isotopes, but on Thursday I figured out a better way to kind of introduce that. So, but this is good just to see what how we get to our atomic mass that we have on these periodic tables. But yeah, like I said, you just pick 2 or 3, just drag your isotopes into the black box there, and you can kind of see what atomic mass you get based on what you've dragged in there. And then you can click on Nature's Mix to kind of see what it is in real life, or like what kind of mix we are dealing with in nature. And again, once you feel comfortable with it, try to answer those 2 questions. Oh, you go with the slider. Yeah. That's a pretty good one too. I remember messing around with the slider a little bit. I think both are good. It's just, it's just cool to see. So is yours touchscreen? Oh, they all are? I didn't even know that. Oh my goodness. That makes life way easier. That's awesome. Yeah, that was weird, right? Because this is only one stable isotope. So in nature, pretty much only exists there. Starting to answer these questions. So I'll give y'all until like about 11:20, or on the 1:20 to finish these up. If you are finished up, and feel free to mess around with, you can click out and go to the other one, the isotope one, just if you want to see like the unstable isotopes versus the stable isotopes. Or anything like that. But yeah, we'll give you about till 1:20. Oh, you get so over this from the first one. You don't really know the first one? Well, let's think about it. So, try to think of the best way to introduce this. So, how did you figure out this problem, right? Yeah. So you made it 70% to 30%, right? So what? So assuming that chlorine 35, they all weigh the same, right? Chlorine 37 all weigh the same, right? And we got this number that's in between the two, right? From there. So I guess what would that represent? Like what kind of math are you doing there?
Average.
Yeah, you're doing the average, right? So you're basically taking the average of what you had there and using it to find your atomic mass, right? So what about nature? Is it the same thing? Just with different? Yeah. So yeah, it's the exact same thing in nature. So basically you're taking the average of the abundances in nature, and that's what you get to your final average atomic mass, and that's what we put on the periodic table. So that's how I would have to word that.
So it's the average of the abundance.
Yeah, so it's the averages of the abundance of the isotopes in nature, the averages of those. I'm trying to think of a good way to word that. Should have written down how I wanted it worded first and then go through that. But really, I just wanted you to kind of get to the point where it's basically the average of the different isotopes in nature and the ratios of those, and average those all together. You get what you're looking for. Because it's not just straight chlorine 35s without KMU. Because you can actually look at that if you just put in like 35, it'll be a different angle, right? If you just put 35 in. Right, yeah, so you get that one, and then you get a couple of 37 ones, so it's really just kind of an average of how much of each is in there. Or like you could say like a ratio is another one. Like a ratio of their masses between. Close to finishing up those two questions. Done. Yes, no.
I'm not done.
Not done?
I'm done.
I don't know if it's right.
What did you say?
I don't know if it's right.
You don't know this, right? I mean, that's the point. We're going to go over it, so. But yeah, I'll give y'all 116. Yeah. I just want to give you a few, like maybe like 1 or 2 more minutes, because then I'll go over kind of one of the problems that I posted online, which is in your notes, so maybe you can look back at it. So So if you are already done, go ahead and pull out your chapter 3 fill-in notes, because we'll be going over one of the practice problems in there. Thought that you do the other one on your own, but just to give you an idea.
I really just took a very big guess.
You took a very big guess on that one? I mean, you did the process, right? So you put 7 and 30 there, and then, so what do you think that represents, that number? So like, how did you, why is this number here and not like up here on the scale or down there on the scale? Probably 35, right? Yeah. So that's essentially kind of what came from the first one, right? It's a non-sensitive measure, so it's like you're basically taking a ratio, right? Yeah. So you got it right. You can be a little more confident. You got it.
Okay,
Yeah. Yeah. It's trust me. It's not too difficult once you see it, and that's why I wanted this activity, because I think that the math can be very overwhelming if you're not able to see it physically and what's happening for that.
Yeah.
So, and that's how we do it for everything, every single element on the table, right? Because I think the actual ratio for chlorine is like 72% to like 20, or it's like 77 to 22% of each. And so I think the average atomic mass on the periodic table is 35.45, I think, something like that. But yeah, just wanted to show what that looked like. Okay, yours done. Think you got a good idea? Kind of good idea? Okay. Go to that. So that's technically like the mass number, right? So basically we're talking about, we'll go over it actually, we'll just go over it in class, but okay, so we'll go through this real quick. So I just dropped that, that's fine. What determines an element's atomic mass? What do y'all think? Taylor, you just raised your hand and then you scratched your back a little bit there, like you were calm. Alright, let me see, what do you got for an answer?
I said it was just an average. Like, I don't know.
Yeah. So you said like it's an average of, so I'll help flesh that out for you. So essentially it's like, it's the average, atomic masses of the isotopes that exist in nature, right? So if we had, for this problem, like I said, we had 70% abundance of chlorine-35, which had its own atomic mass. You had 30% of chlorine-37, which had its own atomic mass. And so what you did is you took the average of both of those and basically how much, or more like the ratio of how tilted it was towards like 37. So we had 70%, 35, 30%, 37. So it raised it what the average atomic mass was.